Steam turbines may differ from one another in size, appearance, and construction, but all of them are similar in operation, and all work on similar principles. During this introductory segment of our course on steam turbines, we will explain what a steam turbine is, how it works, and generally what it is used for. A steam turbine is a machine used to convert the energy in steam into the rotating motion of a drive shaft. These turbines are used because they are simple, reliable, and low in cost to buy and install. Most of the turbines now in use are of the smaller variety, ranging from 1 to several hundred horsepower. Typical uses of these turbines would be to drive lubricating and seal oil pumps, chemical feed pumps, and medium-sized process and water pumps. Medium-sized turbines, from 100 to 500 horsepower, are generally used to drive larger product pumps, fans, blowers, and cooling water pumps. Steam turbines are often used as spares or standby drivers. They are installed to be operated only when the main drivers, generally electric motors, are out of service for repairs, or due to power failures. It is quite common to have a pump in an important or critical service set up with a steam turbine as a spare. These spare turbines are generally operated only about 10% of the time, but are considered very reliable. The larger size turbines, 500 to 1,000 horsepower, are most frequently used to drive compressors and large feed and circulating pumps. Steam turbines are often used as spares or standby drivers. They are installed to be operated only when the main drivers, generally electric motors, are out of service for repairs, or due to power failures. On the other hand, some turbines are used as prime movers, or the principal driver. This 33,000 horsepower monster is used to drive a centrifugal compressor in continuous operation. As you have now seen for yourself, the range of turbine sizes is tremendous. Now that you have seen some examples of steam turbines in operation, let's take a closer look at the turbine itself. There are two basic types, impulse and reaction. The most common type, the impulse turbine, is shown here. The shaft is turned by the force of steam striking the blades, or buckets as they are sometimes called. It's very similar to the way a water wheel works. The other type of turbine, known as the reaction type, turns the shaft by the kick, or reactive force of the steam as it leaves the rotor nozzle. It could probably best be compared in principle to an ordinary whirling lawn sprinkler. It will be helpful if you understand the difference between the two types of turbines. Remember, an impulse turbine rotor is moved by the steam striking the buckets and pushing them. The reaction turbine rotor is turned by the steam leaving the blades. The steam goes one way, the rotor goes the other. All commercial steam turbines operate on one of these two principles, or a combination of both. Since impulse turbines are by far the most popular, we will concentrate on them from this point on in this course. Let's look at a cutaway drawing of a single-stage impulse turbine and study the principle of operation. All impulse turbines are equipped with certain basic parts. They all have a shaft, one or more wheels with buckets mounted on the rim, and one or more nozzles that direct the steam against the buckets. A casing is also needed to confine the steam, and valves are required to control and regulate the flow of steam to the nozzles. The valves are controlled by a governor. The steam flows to the turbine under pressure from the boiler. It passes through the governor valve and enters the steam chest. The steam chest is nothing more than a distribution chamber. It equally distributes the pressurized steam through the nozzles in one side of the chest. The steam flows through the nozzles at very high velocity, or speed. This high-speed steam then hits the buckets on the wheel, exerting force against them. The steam, by hitting the buckets, forces the wheel to turn, much the same as the action of water flowing against a water wheel. The steam then escapes through the exhaust side of the turbine. The turning of the wheel causes the shaft to turn, which drives whatever machinery the turbine is coupled to. It's as simple as that. Turbines can be made with several stages. The type we've been looking at for the last few minutes was a single-stage turbine. Other turbines are multi-stage, with more than one stage. There's something to remember. The number of wheels on a turbine does not denote the number of stages. A turbine with 2 wheels could be either single or double stage. Each stage is separated from the next stage by a diaphragm, as shown. The diaphragm does not move. It acts, in effect, the same as a second or third set of nozzles. As you can also see, there could be more than one wheel in a stage. Therefore, the number of wheels does not necessarily indicate the number of stages. The diaphragms are what you must consider when counting stages. This illustration shows steam entering the first stage through nozzles in the steam chest. The steam hits the buckets and turns the wheel. The steam then passes through the nozzles in the diaphragm and enters the second stage. Applying energy to the second wheel, it passes through the nozzles in the next diaphragm and enters the third stage. After it passes the wheel in the third stage, the steam is exhausted from the turbine. Here's another illustration to show you the path of the steam through the turbine. The steam hits the buckets on the first wheel after passing through the nozzles in the steam chest. As you can see, the buckets are curved. Therefore, the steam is redirected as it leaves the buckets. In order to move the second wheel in the same direction as the first wheel, it is necessary to change the direction of the steam flow again. This is accomplished by the nozzles in the diaphragm, which redirect the steam back in the same direction it was moving when it hit the first wheel. Remember, the diaphragm and its nozzles are stationary. The steam flows through the diaphragm nozzles and jets into the buckets on the second wheel, forcing the wheel to turn in the same direction as the first wheel. This process can be continued through half a dozen or more stages, with the principle remaining the same. Another very important part of all turbines is the constant speed governor. The governor controls the amount of steam that is allowed to enter the steam chest. Since there is a variety of these governors, we will select a very common type which is used on the turbine shown in this module. This is the type of constant speed governor that we will cover in this course. It is called a mechanical shaft governor. The governor assembly is attached to the shaft. It operates a valve which increases or decreases the flow of steam to the steam chest according to the speed of the turbine. If the turbine shaft starts to turn too fast, the governor closes the valve, allowing less steam into the turbine. This slows the turbine down. If the shaft slows down, the governor opens the valve, allowing more steam into the turbine, which speeds it up. The most critical parts of the mechanical shaft governor are the weights. They operate on the principle of centrifugal force. As you can see, the weights on the ends of the rods swing further out as the speed of the shaft increases. It's much the same as swinging a weight around you on the end of a string. When the turbine is not operating, the springs hold the weights close to the shaft. As the shaft reaches operating speed, as shown here, the spring tension is overcome by the centrifugal force of the spinning weights, and they move away from the shaft. In this illustration, the shaft is turning too fast, and the weights are at their farthest point from the shaft. Remember, the farther the weights are from the shaft, the more the valve is closed, cutting down on the steam allowed into the turbine. In this illustration of the entire constant speed governor, the turbine has just been started up. The weights are held in tight to the spindle by the spring, and the valve is in the open position. When the turbine reaches operating speed, the weights are pivoted away from the governor spindle by centrifugal force until they reach the normal operating position. The result is that the spindle is pushed out of the constant speed governor, as shown by the arrows. As the spindle pushes out of the governor, it moves the top of the governor lever to the right. Since the lever pivots on a pin in its center, the bottom of the lever moves to the left, pushing the governor valve partially closed, the normal operating position. If the turbine should exceed normal operating speed, the weights are pushed even farther from the spindle by centrifugal force. They push the governor spindle farther out, and the linkage further closes the valve, cutting down on the steam supply. This slows the turbine down. As the turbine slows down, the weights are pulled back toward the spindle by the spring. This results in the governor spindle being pulled in, reopening the valve, and feeding more steam to the turbine. The constant speed governor stops adjusting itself when it locates the operating speed for which it is set. That's the basic idea of the principles of operation of a mechanical shaft constant speed governor. You are not expected to become an expert on constant speed governors through the illustrations you have just seen, but they should serve as a guide to understanding the basic principles of operation. The final mechanism we want you to become familiar with is the overspeed trip. It is designed to stop the turbine if the constant speed governor should fail. This device is extremely important, since a steam turbine will run wild and blow up in seconds if not controlled or shut off. A very important part of the overspeed trip mechanism is this trip pin. The trip pin on the turbine we will be working with is located in the governor case, which is fastened securely to the turbine shaft. It is actually a pin that extends through the shaft, a pin that is weighted on one end. It is restrained by a spring on the opposite end of the pin from the weight. If the shaft turns too fast, the centrifugal force of the weight overcomes the resistance of the spring, and the weight is thrown out until the head of the weight extends past the edge of the governor case, as shown. The pin then makes contact with the trip plunger and forces it down. When the trip plunger moves, it unlatches the hand trip lever, leaving the resetting lever free to move. A spring then pulls the resetting lever down, forcing the trip valve to close. When the valve closes, it cuts off the flow of steam, shutting the turbine down. There are cutaway drawings of both the overspeed trip mechanism and the constant speed governor in your workbook. You'll be able to study both of them at your convenience until you understand the principles of operation of both. Again, we want to remind you that this brief familiarization does not qualify you as an expert. This training module will concentrate primarily on repair, not on operation of the turbine. But it is necessary for you to understand the basic principles of operation of a machine before you can be expected to repair it. Remember, the turbine is driven by a flow of high-velocity steam, which is controlled by a constant speed governor. If the governor fails, the overspeed trip shuts the turbine down. It's as simple as that. We have some questions for you now on the principles of operation of steam turbines. Please turn to exercise number 1 in your workbook.